So, next topic is filter. At microwave and millimeter wave frequencies, we use coupling theory to design filters, and the method we use, it is called insertion loss method. So, in this method what we do, power loss ratio we define it by using a polynomials. So, here power loss ratio, it is equal to power available from source divided by power delivered to load. So, that is equal to P incident divided by P load. If I consider normalized power values, in that case we can consider P incident, that is equal to 1 and divided by, this is 1 minus magnitude of gamma omega square. So, gamma, it is the reflection coefficient, and if I consider 1 minus gamma omega square, it will represent the power delivered to load. Now, what we do in this method, we actually change the input impedance, or input impedance, it becomes a function of frequency, and that will be varying according to our requirement. For example, if we have to design our one band pass filter, then in band or in pass band, it will have good impedance matching with the source and load, and out of band the impedance mismatch, it will be as high as possible, and it is done by changing the S parameters of this component whatever we use for filter design. So, then among the S parameters, transmission parameter S21, which is a function of frequency, we can write down the transfer function in terms of this S21 as magnitude of S21 square, this is equal to 1 by 1 plus epsilon square into Fn square. Here capital omega, it is a frequency variable. So, for now you can consider capital omega is equivalent to small omega, and epsilon, it is a ripple constant. Now, we define different function for this Fn. Accordingly, we name the filter in different names like Butterworth filter, Chebyshev filter, elliptic filter. It can be shown that for a linear time invariant network, the transfer function S21, it also can be represented by ratio of two polynomials, n function of p divided by d function of p. So, where this np and dp, they are polynomials in a complex frequency variable, p is equal to sigma plus j capital omega. Then we can define transmission loss response of the filter. If we have S21, from that we can calculate what is the loss. It is a positive quantity. So, this is equal to 10 log of 1 by magnitude of S21 square in decibel. So, once we have transmission loss, which represents the loss power loss from port 1 to port 2 for a 2-port network, then we can easily calculate reflection loss for a lossless network. So, LR reflection loss, this is equal to 10 log of 1 minus S21 square. So, for lossless network, S11 square plus S21 squared, that is equal to 1. So, from there, using that relationship, we are calculating reflection loss here. Phase response of the filter phi from port 1 to 2, that is equal to the angle value of S21. Again, it is a function of frequency, and the phase response is very important in particularly wideband applications. Why? Because the delay of phase, it represents, sorry, the slope of phase, it represents group delay. It can be represented as tau d, this is equal to minus del del omega of phi to 1. Now, this is the time taken by your signal to reach port 2. It is a function of frequency, that means this time it varies with frequency. So, if it varies more, in that case we will be facing pulse distortion, and the medium, it becomes dispersive. So, there should be a minimum allowable value for this time delay variation over the band to keep that distortion minimum. Now, we define different types of filter by choosing different types of polynomials. They have their own properties. The most popular one are Butterworth or maximally flat response. Second one is Chebyshev response, then elliptic function response, and Gaussian or flat group delay response. So, let me discuss about one of these. So, Butterworth response, for this one you can see S21 squared transfer function, it is represented by 1 plus capital omega to the power twice n, and if I plot loss which was defined by this relationship L A, this is equal to 10 log of 1 by S21 squared. So, if I plot that, we will be having a low pass type response, you can see here. So, at capital omega equal to 0, loss is 0, and after that it is increasing. It has the property that maximum number of twice n minus 0 derivatives at gamma at omega equal to 0. So, that means here for a lossless system we have magnitude of S21 equal to 1, and from this point if I increase capital omega, then loss it slowly increases, and after omega c, let us call it the cutoff frequency. Omega c is defined where we have a specified loss value L A R. After this, loss increases rapidly. So, this is for a low pass filter. We can design band pass filter by using low pass to band pass filter transformation. Next, another example, this is for Chebyshev response. You can look at the plot. We have ripple in pass band, and in stop band we do not have any ripple. So, it exhibits equal ripple pass band and maximally flat stop band, and the transfer function is defined as 1 by 1 plus epsilon square into T n square, where epsilon, this is called the ripple constant. It can be given by square root of 10 to the power L A R by 10 minus 1. L A R, this is the specified loss value. For example, you can define your cutoff frequency omega c by 3 dB. In that case, L A R that is equal to 3 dB. You can define your cutoff frequency by, let us say, 0.1 dB. In that case, L A R that is equal to 0.1 dB. So, T n, this is a cosinusoidal function or cos a hyperbolic function depending on the omega value. Now, if I compare this Chebyshev response with the previous one, Butterworth low pass filter response. So, you see in pass band for Butterworth we almost do not have any variation, whereas for the Chebyshev we have ripples in the pass band, and for the same order we will discuss later, we have higher attenuation slope for Chebyshev response. So, if attenuation criteria is more prominent than the passband criteria, in that case we can choose Chebyshev low pass prototype response. But for Butterworth polynomial, we have one advantage. If we plot the group delay variation, it will have lower variation compared to the Chebyshev one. So, for wideband applications, then Butterworth should be preferred if we want to avoid any dispersion. So, in this regard, you can use Gaussian response, which will have a flat group delay, theoretically no group delay variation over the whole bandwidth, but its attenuation response is poorest among all these four. And this third one, elliptic function response, it shows ripples both in passband as well as in stop band, and it is having maximum group delay variation inside the bandwidth. So, next how to realize these functions. So, we start with low pass prototype. So, considering, you see, if I ask to design a low pass filter using lumped element like capacitors or inductors, how we will be connecting. So, capacitor usually we use in shunt configuration. So, high frequency component will pass through capacitor, and inductors we will be using in series configuration. So, it will attenuate high frequency components. So, the basic low pass filter configuration, it can be a pi type or a T type configuration. So, in this case we are showing both of these two different types. In the first type, where we are using a basic pi type, you can see two capacitors separated by one series inductor. Now, these elements usually they are represented by their normalized values, we call simply G parameters, G1, G2 to G3. If n is even, then last element will be one inductor, and if n is odd, in that case last element will be one capacitor. And you can see G naught and G n plus 1, they represent source impedance and the load impedance represented by two resistors. We have dual of this. In this case, in place of pi, we are using a T network, two inductors G1, G3 and one shunt capacitor given by G2. Now, if n is even, in that case last element is a capacitor, and if n is odd, in that case last element is one inductor. So, we have actually different tables available for these G values for different LAR, specified LAR for different types of polynomials. Here, for example, we are showing the element values for a Chebyshev low pass filter, where it is considered that LAR equal to 0.01 dB. Okay, so, let me discuss one point, how to define this LAR. Better let me draw it. So, let us say we have a two port network. This is port 1, this is port P2, and it is behaving as a low pass filter. Now, if I plot S21 versus frequency, so along x axis I am representing frequency in gigahertz, and along y I am representing magnitude of S21 in dB. Now, if we have perfect transmission from port 1 to port 2, so that means S21 in dB, it is 0 dB. And since we are considering low pass filter, as the frequency increases, in that case attenuation increases, or S21 in dB it becomes negative, goes to minus infinity. Now, how to define the cutoff frequency? Let us say I am using this low pass filter to separate the IF, and my IF requirement is 100 megahertz. So, IF bandwidth minimum we need 100 megahertz. So, whatever signal we have, it is in this 100 megahertz, we do not want any attenuation for this 100 megahertz signal. So, we can define LAR, let us say 0.1 dB or 0.01 dB, and it should have at least a minimum value FC of 100 megahertz. So, LAR, then we define LAR, this is equal to let us say 0.1 dB. Now, in filter applications, many times we simply define 3 dB cutoff frequencies, but not here. If I define my 3 dB cutoff frequencies at Fc equal to 100 megahertz, that means already I am assuming that my 50% power near the cutoff frequency, it is being attenuated by the low pass filter, which I do not want. So, when I define LAR for this cutoff frequency, it should be much lower. Now, to have some specified attenuation at some given frequency, you can define one more cutoff frequency. Let us say for this application we need at least 30 dB attenuation above fc equal to 1 gigahertz. So, in that case you can define another cutoff frequency, but you remember whenever we are going to use these charts, this table, we first consider what is the signal bandwidth, and accordingly you can choose LAR equal to let us say 0.1 dB or 0.01 dB or 0.001 dB, anything. Now, after fabricating this filter, so whatever bandwidth I am defining, let us say 0.1 or 0.01, it can't be measured because of fabrication tolerance and also the accuracy problem of VNA. This S21 it will vary inside the passband, and this variation will be more than let us say 0.01 dB. So, that is why it is really difficult to measure that 0.1 dB or 0.01 dB bandwidth of a filter, and practically we measure 3 dB cutoff frequencies. It is easier to measure. So, now let us go back. Now, you see in this low pass prototype filters, if I use one single pi section, obviously attenuation will vary slowly. So, if I want to improve this Kerr selectivity, that means the attenuation roll up, in that case we have to increase number of sections or we have to increase the order of the filter. So, we have to use more number of elements. This table it shows till g equal to 10, g naught it is, they are all normalized values, g naught this is equal to 1, and omega c it is considered as 1. Then for example, let us say if I consider n equal to 2, we have g1 equal to 0.4489, g2 equal to 0.4078, and n plus 1 that load 1.1008. Similarly, depending on your attenuation requirement, you can choose the order of the filter. For example, let us say you decided your order of the filter at least it should be n equal to 7, then you can choose these g parameters, this particular row. Now, we have to realize these g parameters or L and C values. So, similar type of tables available for different LAR values and also for different polynomials. Now, practical filter design. So, already let us say we have the required g parameters, we have to now find out then what is the actual L and C's values, because the g parameters those are normalized values given in chart. So, for that we have to use some sort of impedance transformation. Next step, we have used omega c equal to 1, that is again normalized value. So, we have to use one transformation for our required fc. So, the example which I was showing, fc equal to 100 megahertz. So, then the practical steps, you first change capital omega to practical frequency small omega, then the change terminating impedance to port impedance z naught. Previously it was shown by g naught and g n plus 1. It requires obviously impedance scaling. So, how we define impedance scaling factor? Gamma naught, this is equal to z naught by g naught, when g naught is a resistance, and it is equal to g naught by y naught when it is a conductance. So, typical z naught values for any millimeter wave system or microwave system 50 ohm. Next, we have to find out the real LC values. The prototype elements are transformed as L, this is gamma naught equal into small l. So, it is actually that g parameters, then capital C equal to small c by gamma naught, again this right hand side C, this is the normalized g parameters. Similarly, we can find out the real capital R and capital G all the right side they are the G parameters. Let us consider then how to design a band pass filter directly. So, for band pass filter design we use resonators, coupled resonator systems. So, obviously it will be a 2-port network, port 1 and port 2 they are connected to my millimeter wave systems, which is 50 ohm system. So, in simulation we can represent then port 1 and port 2 by the equivalent resistance 50 ohm, and then power should be coupled from port 1 to resonator. So, we have to study this coupling mechanism in details, and how the filter design steps it can be represented in terms of this coupling. So, what we do, the coupling from port 1 to first resonator or port 2 to last resonator, we represent it by quality factors. We call it external quality factor. So, let me show you in diagram. So, here you can see the input port, input feed line and the output feed line. We are considering a 4 resonator systems. So, this is a conceptual diagram. Then the power transfer from feed line to resonator 1, it is being represented by external quality factor QE1, and for the nth resonator to feed line it is being represented by QEN. And then the coupling between two resonators, it is represented by coupling coefficient. I will discuss later what is coupling coefficient and how we can extract the values by using any full wave simulator. This coupling, it can be electric coupling due to the electric field, it can be magnetic coupling, or even it can be mixed coupling. So, this is a complex situation, and the relationship with prototype LPF elements, I am showing you directly the values. QE1, we can relate it to that G parameters. This is equal to G naught G1 divided by FBW. FBW represents the fractional bandwidth. So, if you have the bandwidth, then simply bandwidth divided by this midband frequency, it will give you fractional bandwidth. QEN, this is the external quality factor for the second port. This is Gn into Gn plus 1 divided by FBW, and the coupling between I and I plus 1 resonator, that is a function of fractional bandwidth and the G parameters. So, FBW divided by square root of Gi multiplied by Gi plus 1, where I it varies from 1 to n minus 1. So, you see then if we need higher fractional bandwidth or for wideband design, we have to obtain higher coupling. So, for any given specification, then how to implement any filter. So, this is we call synthesis steps. First, we have to choose the type of polynomials depending on the requirements, passband let us say group delay variation, passband S21 variation, then stop band attenuation requirement, skirt selectivity. Depending on all these criteria, we can choose the type of polynomials. It can be anything, Butterworth, Chebyshev, elliptic, or flat group delay or Gaussian response. So, if nothing is specified, you can select Chebyshev response most probably, because Chebyshev it is somewhat in between Butterworth and elliptic. Then determine the low pass prototype elements from that tabular data, that means the G parameters. Then calculate the coupling coefficient. So, you have to determine number of resonators from order of the filters, and then the required coupling coefficients, that means the coupling matrix basically you have to synthesize. So, M I and I plus 1, it is already defined, we discussed previously. Then determine the external coupling parameters, choose the type of resonators. So, it can be of different shapes, and implementation also, it can be in microstrip line, it can be in let us say image kite, it can be in rectangular waveguide, anything. So, depending on again power handling capability capacity, depending on loss requirement, we have to choose the proper implementation scheme. Next, determine filter dimensions. So, this filter dimensions we have to use some sort of full wave simulator to realize this filter, and then the optimization for final design. So, it is a lengthy procedure, and it starts with the Q, E and K calculations. So, here what we will do, we will assume that we have the required G parameters, and from that already we have calculated the external quality factors and the coupling matrix. So, next we will discuss then how to implement this filter after a short break. Thank you.